Hello guys, how you doing? I hope you're enjoying DotNext so far. So here I come to make your day a nightmare. So it's a good thing that we can be here today. I really like to say thanks to the DotNext conference for it. So we're going to start with a little bit of history here. We were like not long ago in a city not that far away named Moscow. And we were talking about something that it may sound like a big number. 20 billion operations per day. It's a kind of big number, so I usually write it down like 20B, just in case. So the interesting thing is about a few calculations later, we ended up with a number that actually made sense. 5 milliseconds. That's a caveat. We are talking about per operation per node. So this was more or less about the budget that we had in average to actually achieve that particular target. So we were everybody like, whoa, we can actually get there. So, but the problem is that on the eve of 2018, we are talking like 3 of January. I was like in the beach, taking my vacations. I was like here with the water like in here, and I get a message. What I was doing with the phone in the water, well, ask Dylan about that one. So these two ugly guys get up in the scene. I don't know if you heard about them, but if you didn't, they're kind of an issue. So at that time, it was like I got this message from my colleague that said, I don't know what you are doing. You just have to read this. So he sent me this link. There was rumors at the time. This was pure speculation. It was like there was no information whatsoever of what was going to happen, but it was going to be released on the 10th of January. So we were 7 days ahead. This thing was going to make my life a nightmare. So if you don't know what it means that someone figured out how to get inside the processor, figured out and how to get information back from the branch predictor, we are going to talk about. So that immediately that made all CPUs that you have around like open for investigation. So anyone can just go and grab your passwords or do who cares. So there was something here, OK. So by the time this thing gets to be patched by the OS and the CPU guys, there were some things like this. This is actually a post that the Epic Games team did for Fortnite. This is what happens on the exact day of patching. So they went straight from a typical 10%, 20% CPU rate straight to 40, 60. That means that they also having trouble getting people logged on to the service. So they wanted to play games, and they couldn't. So it's an interesting thing that this happened because it sounds like, as an engineer friend of mine sent me the other day, it's like there's nothing funny about these two guys, except obviously the jokes. So we got these guys that actually designed a new Moore law. And the problem is, it may look like a joke, but it's not that far from the truth. So the thing here is that even though it sounds crazy that I'm talking about Meltdown, that's probably something for a security conference. Meltdown isn't an excuse here to talk about something that actually made a newspaper headline. It is actually a reminder that hardware is not getting faster at the rate that we are consuming and the rate the data is being processed today. So what we are seeing here is that we have been cutting corners on hardware design for a long time just to make things fast. And suddenly, from one day to the next, they become risky. So to rehash an old saying is the free lunch has been over for a long time. And we actually have been running on borrowed time. So it is time that we actually decide effectively to go and look to the kind of code that we write and the kind of tool sets that we have, because we will have to pay eventually. So in a sense, if you're not investing in performance, you are essentially transforming money into heat, which is cool if you want to warm your building, but definitely not good for business. So as in all conferences, I like to talk about the things that I'm going to give for granted here, because this is a hardcore conference. I actually have a single slide later that you can use as pointers to get to know this kind of stuff. But the things that we are not going to talk about today are things like, it's OK, the just-in-time and the compiler are usually good enough. Yeah, we can make a statement for that. That's true. So what we are talking about is what happened when it doesn't, when they are not good enough. And it's our job to actually get them to do the right thing. Also that most of our software is littered with cache misses and memory effects, which, when you go further in the optimization efforts, are going to dominate your software runtime. So there's like an entire zoo of different memory effects that you will find along the way. So we are going to actually talk about some of those animals. Also, that you have to be aware of the data dependencies. There was a very interesting talk by Andrei Alexandrescu that talked specifically about that. And also, you are not required, and I like to stress this part, to know the instruction set. The instruction set is huge. The difference between one processor line to the next processor line, even if the same instructions are in there, their behavior is quite different. So what you do, you use a cheat sheet. I do not know the latency of particular instructions. I just go and look them up. And also, there are very interesting applications that you can use inside Visual Studio or other IDEs, like, for instance, ASM Dude, that are going to show you that straight from the debugger window. And of course, because we are doing a hardcore talk, all tricks are allowed. Nothing is outside of what we can do. So this is, I like to actually be pretty clear here. If you have to micro-optimize, make sure there's no other way. We ended up here because there was no other way. So this is definitely not something that you would do like typically, unless you are in a situation that there's no resort. But the actual process of investigation that I'm going to lay out here, it's actually useful when you have to diagnose these kind of problems, because it is exactly the same at the architectural level or at the algorithmic level too. So we are going to talk about a very, very, very simple algorithm today, which is, and I keep pressing the wrong button, div in memory. It is like this simple algorithm. You just get a chunk of memory, another chunk of memory, and check what changed. But the thing is that simple algorithm is the core of a journaling system. You need to know what the user wants to write in a transaction to actually write it to disk. Because if not, you are going to say, oh, this byte changes, and we are writing like a megabyte in there. It doesn't make sense. So div in memory, it's a very, very, very simple algorithm. You will see it. We can actually pack the entire code, or almost the entire code, in a slide on the surface. So, and it also happens to be in our critical path. When we hit that particular place, there are write transactions waiting for us to actually be saying, OK, I can continue. It also shows along the process of actually optimizing this thing a lot of different bottlenecks, and that's the interesting thing. You will see that there's this mix and match and back and forth between the different CPU subsystems, so you can actually see that behavior. Also, it's interesting that a single loop takes 99.9% of the total execution time. So we go for the loop, and we are done. So without further ado, this is a rage age talk, and we are going to start from here. So if you think that this is too much, you can still be here. So we are going to talk about a very, very new development here. CoreCLR had enabled single instruction, multiple data instructions, like mapping a particular method call into the actual instruction, because there was some availability through numerics recently. Like the code that I have here didn't work 3 weeks ago. The guys at Microsoft and Intel were great in that they actually built the support for the instructions that I needed for this talk before the entire subset of instructions. The interesting thing is that this API, in a way, mimics what the C++ intrinsics are. So those that come from C++ or assembler will feel natural, the pass from one to the other. And the interesting thing is that, differently to many of the .NET library approaches, this particular library has a shoot yourself in the foot kind of design. I could say you're not going to shoot yourself in the foot, you're probably going to blow your leg, but that's a different thing. The good thing is that this is also available. Like 1 week ago, it was published, the preview of the runtime that support the complete SSE and ABX instruction set. So this opens up a new dimension of optimizations you can do to your code when you really need it. And this is interesting. So without further ado, I present you our div algorithm. So the idea here is that Dylan's cat has been under the table on the last state. But in the new state, she jumped up and went over. So as we are a transactional database, we had this transaction, and we have to record the event. The thing is that for that, we have to scan the entire thing. How we could scan it? Well, the T and the T are equal, so we move to the next one. Now, the H and the H are equal, and we move to the next one, until eventually we hit a case that are different. So at this time, we already know that we have moved 8 steps. Our index moved 8 steps until you hit that particular case. So as U and O are different, the new state that I want to record is O. So we pass to the next one again. So now N and B are also different. So we write it down. Eventually, we write everything down. And you may notice a 4 there. Because the buffer ends there, we just close it up. But it's the same case when you actually hit a now they are equal. So now you stop and say, OK, I started at 8, I read in 4, and this is the data. So this is a simple encoding. You can actually change the encoding. This encoding happens to be interesting for the database use, not for presentation purposes. So without further ado, I'm going to show you the simple algorithm to handle this. So this is the kind of code that definitely is not the one that you will see for an example of this algorithm. So we are going, don't worry, we are going to go in one step at a time, understanding what this is doing. So we have here that we are getting void pointers because we don't know what it is, but we know we want to treat them one step at a time. So we actually go and say, OK, this is a byte pointer. And then we have our big for that it's going to move along the way through the buffer, which has a size, until, well, there's no more buffer. That's essentially what we have there. Then, when we have to move forward, because there's nothing happens, so it's OK, what we are going to do is, OK, we are going to get the byte from the new and from the modified. We are going to check if it's different. If it's not, we are going to go else. Have we started a new, are we already in the process of writing down stuff? No, we are not, because we don't have anything. So we just skip over and go back to the top of the loop. So pretty simple loop, two conditionals, we are done. Interesting thing is, when the memory has changed, and we actually had to record that stuff into our buffer, now this gets interesting because M and O are going to be different, so we are actually going to be writing this particular stuff back into the buffer and move the pointer so the next one is going to point to an empty space. And this is the case where, OK, we were been doing stuff and nothing happens. Now, OK, this one is the first that is different. So as it's the first that is different, we are going to write down the location when this started. And we are going to say, yes, it started true. Then, obviously, we are moving into writing that particular content as it was in the other condition. The same happens. The symmetry is how we are closing that particular case. So the interesting tidbits of this is that this works byte by byte. We are going one byte at a time, getting the data, writing the data, and we're done. Just to give you a reference, this algorithm is able to process 700 megabytes per second on my reference machine, which is an Intel i7-7700, a Kaby Lake for the guys that write this kind of code, so you can actually go and look into the tables. And it has 32 gigabytes of DDR4 running at 2400 on dual channel. Remember about that, because it's important. So can we do better? What do you think? Oh, you got the trick question one. OK. So what we're going to do is we are going to use a tool that's typically not part of the arsenal of someone that is doing optimization, because its actual use is when you have to go deep down and to understand what is happening at the hardware level, which is called ptune. So the interesting thing about ptune is that it has 1 million hardware events available for you. And this is just a summary. So as you see, we have like a bunch of stuff in here that we are going to discuss in detail. So we got a CPI, which is how many instructions you can actually execute at the CPU level per clock cycle. Just to give you an idea, a number of 1 is considered good in the high-performance community in HPC work. And the theoretical best for this particular, and probably for a few generations more, this particular CPU is 0.25, which means that we are able to execute simultaneously 4 instructions per cycle. And we are quite well. It is also telling us that this problem, this algorithm is core bound. It's computationally bound. So it's not you, it's the CPU. It's also saying us that our CPU is running, it's retiring instructions, which means that it's able to execute 53%. It means that more than half of the actual processing slots, while it is executing, are already covered per cycle. And it's also telling us that for 29.9% of the clock ticks, it was able to execute, to have in execution, in simultaneous execution, more than three or more instructions at the same time. So this could be considered a pretty good metric, right? So what could possibly go wrong here? Any idea? Well, it just happened that these guys do really know what they are doing, and they are just a little other very complicated, not complicated, but hidden feature. That is that you're able to see how you're using your memory. So essentially what this is telling you is that we have been able to transfer memory back from the memory system to the CPU for use at a rate of 1 GB per second, which makes sense. We are able to process 700 megabytes. We are more or less there. But the thing is that I mentioned we are using a dual channel memory whose burst rate is around there. Granted, it's not sustained, but that's the maximum that you can get. And even if we have been running on a single channel memory system, we still should be in the burst rate around there. When our best observed is around there, and it's basically an outlier. So as you see, we have a lot of room for improvement. So what do you think would be a way to fix this? Anyone? Reading in chunks, yeah. So we are going to call the reading in chunks a better naive div. Why? Because essentially, it's like the very first idea you can figure out after you have your naive. You're going in a single, then obviously you can move in chunks. So essentially, we use word chunks, which means the maximum amount of space that you can use based on your instruction set. So in this case, we are going to use 4, because if I use more or less, either it's going to be too long or we are going to outgrow our own buffer. But the idea is eventually we write our index, which is 8. Then we move to the next, because we figure out these ones this block is different, and we write up our block. And then, obviously, we finish our buffer with the size of what we have actually written. So, but the question is, what is the word size? Because, OK, we know our current CPUs have word size of 32 bits or 64, depending on if you're using one or the other. So let's talk about what you can actually use today. We are not talking previous stuff. We are not talking today. Today we have longs, which is our biggest thing out there as a single primitive, or we have system numerics, which has a little bit of trouble. You cannot know if it's going to be 16 or if it's going to be 32. It would depend on where you are running and a lot of interesting reasons. So you have no control, and also the only stuff that you have is load the store and some arithmetical operations. But on CoreCLR 2.1, we actually have like, OK, these are the quantity of bytes that we can deal with, which is 8 for our long, 16 for SSE, and AVX 32 bytes. And in the future, I hope not long, we can actually go 64 bytes at a time using AVX 512. So you remember this part of the algorithm. The algorithm is simple. We just move around, and we are done. So we have our load and compare part of the algorithm. We also have our stride, how far we are moving the pointers every single action, every single iteration. And we also have the place where we are actually going to write to our buffer, the buffer that is going to encode the information. So this is how today, with review bits, could look AVX implementation of this algorithm. We have our load and compare, which essentially is we are going to load 32 bytes here. We are going to XOR and test. These are really two operations at the processor level. That's the way you do a distinct. And we are going to do a store. We're actually going to instruct the CPU to write this into this particular place in memory. So this is what Bitune has to tell us of this particular algorithm. You see that the changes are not that big. It's kind of simple. The interesting thing is that we went from 0.3 straight down to 0.8. That's not good. We are still in HPC range, but we had regressed a little bit. It also went down from 53 to 26 in the amount of actual execution work that the CPU had to do. That's not bad. And then we're going to look at our ports, which are the actual execution units. So what we see here is like, OK, we're done. Only 8% of the time, we are actually being able to feed the processor enough stuff to do. But this is interesting. This is new. We are memory bound. We used to be core bound. Now we are memory bound. So at least stuff changed. But when we look at this, now you see a difference. Now we are, on average, on 50 gigabytes per second. That's quite a difference. So we're actually approaching the theoretical burst rate for single-channel memory, for my particular single-channel memory. So as you can see here, the memory thing is, OK, we did the improvement. I'm going to go ahead of myself. Yes, it's an improvement, and a huge one. But what we are seeing here is that we ended up in another bottleneck, a different one. But the problem with this bottleneck is that there's a big zoo out there of the things that can happen with this particular bottleneck. You have many levels at cache. We can talk about cache L1, L2, L3, non-temporal, and also the DRAM itself as main sources of problems. It is also very, 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 very slow in terms of being able to move stuff around from the DRAM back into the CPU. And the problem also is that it's not getting much faster than what we have today. The best memory you can buy, its bandwidth is not that good either. So we are like kind of stuck. It's also very difficult to measure, and this is very important because we are going to be facing this kind of stuff. It's very difficult to measure and to isolate the effects caused by being near the max bandwidth. What happens if you're near the max bandwidth and you want to measure, even the process of measuring it, not talking about Outlook deciding to go to check the email, it's going to modify and it's going to skew your distribution because now someone is competing with you to actually get that bandwidth. So it's kind of a big issue. But before moving further into the talk, we need to know our tool, what we are dealing with. So we can actually say there's 3 things. We are going to talk specifically about 2. But the interesting thing here is this is the front end. This is where the CPU prepares the data in such a way that it can pass it to the backend, which is able to execute this stuff. So actually, the very first part of the CPU, it's only preparing the instructions you give them as data to be sent to the actual execution ports where they eventually execute. So the place where the magic actually happens is in that dark green part of the backend. So as you can see here, the front end is not a simple thing. You can see that, for instance, you have your instruction cache, which is this cache is going to get to try to go ahead from you and get the instructions. So whenever you need them, they are in the cache, and they are going to be pushed faster into the instruction fetch and predicode section. The predicode has, for instance, 2 lanes. If you're running on hyper-threading, which means one physical core is actually able to execute 2 tasks at a time. Or if you are not running with hyper-thread enabled, where all 50 are for you. Interesting here. If you time your algorithms with hyper-threading and without hyper-threading, the behavior is different. Then it comes the decode part, where your instructions are going to be decoded into microinstructions, which then are going to be either put into the microcode sequencer, which is like, oh, this instruction is like 100 instructions, so they go to the microcode sequencer, and then the sequencer executes. Or they go straight into the allocation queue, which is the thing that is down there. So you also have our friend, a meltdown friend, which is the branch predictor, which is trying to get ahead of himself, trying to get more instructions, and try to to figure out what are the next instructions that are going to be executed just in case. Here, what we have is how everything gets executed. Eventually, those instructions we put in the allocation queue are going to end up into the rename, allocate, and retirement. That's where there's a very interesting thing. For instance, if you move one register to another register, so let's say you move from the RBX to RAX, how many cycles do you believe it is needed to do that? There you have it, 0. Why? Because it's actually a rename. I don't need to move the physical thing. And the question is, why that happens? Because the actual physical registers that you have are 180 for this particular platform. So it is a lie that you have 15 or 16 registers, because you actually had 180 physical registers. The same happened with the vector registers. So now we figured out, OK, not only we don't have a huge amount of registers, they are also different, in different allocations. So you can have this beautiful algorithm that only uses vector instructions, and you are bounded by there. And there comes the magic here, where everything is executed. Interesting point, not everything executes the same. If you put 2 instructions, one after another, that uses the same port, they will have to wait. So you can actually exploit that knowledge to actually lay out the instructions in such a way that they intermix so they can be executed at the same time. So with knowing that the problem is our memory backup, that we don't have problems at the front end, we don't have problems at the back end, we actually have problems at the level of getting memory to the CPU. What should we do? Prefetching. So we are going to ask the processor, hey, you know, I'm going to use this like 100 cycles from now. So let's better get it out. Let's bring it here so I can do something with it. So the question here is that in here we have like this knob that we can actually tell, OK, get this. The question is, where do we put that? And how far ahead I have to go to look? So you may notice the red stuff in there. So we are using CoreCLR intrinsic support to tell the CPU, go and get this memory. But how would you solve this problem? What do you think? There are two ways to do this. Either you're clever, or you brute force it, which is like trying them out. So this is how the different offsets behaves for every single cache level that you want to try. So OK, now we know 2K ahead is where we are going. So we actually do that. We get the number. We put the constant in there. We compile. We run both under btune, and what we get is this. 24% memory bound against 51. L3 and DRAM 2 and 4. So definitely we are not having problems anymore about getting stuff back to the CPU. Another interesting measure that is going to tell you that is that the LLC miscount goes from 900 million to under 2 million. It's like coming from a lot to nothing. So it actually has some other more complex effects that if you want I can explain later. Sorry, the online guys on the discussion zone. It's why the stores go down. So just to give you an idea of what this means, we run all of them. So we have our naive attempt with the byte. We move to our long implementation, to our 16 bytes implementation, to our 32 bytes implementation, up to the 32 bytes, including the prefetch. So we went straight from 700 megabytes per second to over 10 gigabytes per second diffing. I also added a scalar version, which means it's an 8-byte version, applying all the tricks that we are going to also apply to this particular implementation, which is able to process 9.2 gigabytes per second. Our current implementation actually is able to handle only 7, because I didn't PR yet the change. So just to give you an idea, this is the difference between the actual naive with the optimal prefetch. You can see as how, and that's why these kind of distribution graphs are so interesting, because you can actually see the difference. You can have the numbers, but this is visible. So, can we do better than this? You think so? It's going to get hard. Well, the better question, do you really want to do more than this? So yeah, we can. So we can optimize the actual code layout, because now we are not memory bound anymore. So, and we are also not CPU bound. What we are is like CPU starved. We don't have things to work with. So there's actually some interplay between the instructions in there that are causing this to go haywire. So we actually have to focus on how instructions are arranged in our compiled code, not in our C# code. So we also have to make sure that we are using properly the instruction cache. We are actually issuing instructions that are easy to decode, because complex instructions mean complex execution. And also, we can actually check if we are using the loop stream detector of the newer CPUs. Fun fact: Kaby Lake and Skylake has a disabled loop stream detector. Also, we have to take care about what type of instructions we use, because latency may be different, reciprocal throughput too, which means how many instructions I am able to execute simultaneously. For instance, there are instructions that whenever you execute them, they may have a latency of like around 10, but they have reciprocal throughput of 2, which means I can execute one instruction every 2 cycles. Also, what physical ports are actually in use, and data dependencies. So you remember this. We talked about this. This is like the base algorithm from now on. Interesting question about this is that we have our load and compare here. We have our strides. We have our writes. So we can actually go there. This is the actual output of a nightly build. So you can actually get the same output from the preview one. I have a nightly build here. But essentially what you have here is what usually the just-in-time compiler would throw at you when you compile this code, with a few ranges to make it more easy to understand. But essentially what you have is this. We have our prefetch, where we are going to prefetch something. We are going to calculate the location, and we're going to prefetch 4 instructions. We are going to have our main loop, where we are going to get that data from memory, do an OR, check if they are equal or not, and then jump to the proper place. If we have to store, there's changes, they're different, we are going to store that data straight back into memory. We are going to the end of the actual for loop, where we are going to increase the sizes of our indexes. And of course, we have these 2 guys with the start and the end in there. So how our loop looks when unchanged? Our loop looks like this. We started here. We test if it's started or not, and if it's closing or not, and then we go to the end of the loop, and so forth. So we are moving in circles. But look at this. We have 3 additions here that actually happen here. And immediately after, we are using exactly the same thing there. That's bad. Data dependencies. So the good thing is that the less code that you have, typically it's faster, typically, not always. But data dependencies are like the big problem. So let's look at it. This is essentially our data dependency. We are going to increment that stuff, and we are immediately going to use it. So if we could diminish the amount of those, could be interesting, right? The interesting thing is that, yeah, we can. This is a trick, a very interesting one, which means that I'm going to use a single pointer I'm going to calculate the distance between this pointer and the next pointer. And then I'm going to address everything as pointer plus offset plus, well, in this case, in the case of the prefetch, the distance we want to fetch ahead. So in our load and compare, what we have is that we are using that particular semantics. This trick, while it looks cool, actually works better with a scalar code, not with this kind of code, the AVX or the SSE. I'm not going to enter into details on how this works, on how that is. I'm just going to say for the online guys, so they can look it up, it is because of indirect addressing. So if you want, then we can talk about it in the discussion zone. So essentially what we have is we got rid of those two, and we added those two there. Not interesting, right? So in the end, we got rid of only a single arithmetic instruction. So one instruction less. Now, let's look again at our code, our new code. So this is our loop when we don't have change. When we are like running fast, trying to find something that has changed. And this is our main loop when things had changed. So I'm actually writing back into my output buffer. Can we do better than this? Seriously? Yeah, we can. I don't know if we want to, but we can. So, where in the world is the hot code? Can you guess? So, we barely know that more or less this part of the code always gets executed, so we are always prefetching, we are always testing, so yeah, this is clearly part of the hot code. But then we figure out, okay, if we are testing this, we actually have to go ahead with it, because if I took that branch, I have to go there. And also, we know that the end of the loop always happens, so it's also a part of our hot code. So essentially, this is our hot zone. But the thing is that it's a bummer, right? This guy and this guy. What if we make them disappear? So it just happened that here, this is actually more complex than that I could actually solve. I actually had to shoot an email to one of the just-in-time engineers. So how can I get rid of this? Because the just-in-time refuses to do this. So he actually sent back this code that has a way to get rid of that particular code. So meanwhile, they figure out how to expose this for us, so we can actually do this kind of stuff without much hacking. I'm going to show you how his version of the algorithm behaves. The interesting thing about this is, look at there. This instruction, which is getting stuff from memory, actually had a big of a problem, which is you got this guy that is in charge of actually going to get the data from the cache. So this instruction comes to say, hey, I want the data. No, I can't. I'm programming. Hey, no, I don't. No, don't bother. So eventually what it happens is I said, OK, I will go. He goes, and he figures out, OK, it's not here, it's not there. Oh, I have to go there. So by the time he comes back, the other guy was already sleeping. So the interesting thing here is that only 31% is actually DRAM bound. And the latency you actually have is 1.7%, which means that only 1.7% of those instructions are bound by actually going to memory. So the problem is between L1 cache and L2 cache. We seriously cannot feed it faster. And this is what the documentation actually says about this particular metric, which is it's usually, as you can see there, caused by prefetches, right? If you had this trouble, check if you are doing prefetches. So what you could do? What do we do when we have this issue? We just go and try them on. So we try them, and no, it's not prefetch problem. So no, the maximum is actually, and you will see here. Oh, I forgot the code, by the way. This is our code. Looks nice, right? Let's do something. This is the actual hack. So what you see here is that we have a label there that says stop. And we have this guy that says go to start block in that particular case. The interesting thing is that the just-in-time compiler, if we do not put that particular early break that I'm going to explain now, she decided that it's going to put the start block in there and the block in there. So and there's no way to convince her otherwise. But this particular code is interesting because what Andy has been doing here was he said, OK, let's replicate our loop code, and let's jump to the top. So essentially, we put 2 copies of the actual loop code, a for code, and we loop back. Because we are looping back, basically the just-in-time compiler says, OK, no, I cannot put this here because it doesn't make much sense. So OK, I'm going to put it where it's supposed to be. So up to this point, it looks like I don't want to go that far right. But the thing is that it doesn't have to be that way. There are facilities. I actually did a proposal 2 years ago to fix this issue, this particular issue, which is I can tell the just-in-time, hey, what about I can tell you which part is hot and which part is cold when you have an if statement. So if you want to see this, you can actually go to the issue and vote for it. Probably it will get picked on for the next version. Who knows? But the thing is, the code that you would actually have to write to achieve the very same thing could look more like this. Makes more sense, right? So we are going to I have a final thought on this, and is if someone says that you can't write fast code in C#, you know the answer, right? They should come to DotNext more often. So with this, I open the questions if we have enough time. I think that we have, because we have 5 minutes. Any questions? Complicated stuff, I know. Don't worry. Oh, yes. I don't bite. We have a winner!
Yeah. Thank you for a great presentation. I got lost in 15 minutes. Got frustrated. But yeah, the question is, in the very beginning, you just mentioned Spectre and Meltdown, that
Yeah.
it will cause a lot of problems.
Yeah.
And I read that it will cause problem to databases, and you have a database,
Yeah.
and how hard it hit you.
The problem is the following. Meltdown causes like an escalade of things that you have to do to actually fix it. One of those, and this is not a small thing, is they had to actually change the kernel code to separate everything, every OS information that has been mapped back into the user process. So that means if it's outside of my user process, of the user space, I cannot know what's the direction in memory, the physical direction in memory the OS structures are sitting. So you can actually avoid Meltdown and Spectre because now the attacker is not able to know where the OS is. So it was like obscuring the stuff. But that caused the next thing is that many things that happen that could be done on user space now are not possible. You actually had to trap to the OS, making all your context switches to the OS more costly, which means every single time you do I/O is worse. And every time you do I/O, you have a problem. Because we are the database. We do I/O all the time.
Yeah, and the question is how much?
How much?
Yeah.
Around in between 10 and 15.
Okay.
If you want the actual number.
Thank you.
Anyone else?
Yeah, thanks for great presentation. I have a question. How many loops do you expect on this for loop you described? And the second question, do you thought about using maybe OpenCL? You can just push your calculation a bit lower. Yeah.
Yeah, I get the question. First question. The smallest page that we have is HK. So there are a lot of loops, if that's your question. But you can go higher, because if data is bigger, you just go there. Just to give you an idea, do unrolling is not going to save you in this case. It's going to save you, actually, the implementation for the Scalar version, do 4 times rolling. To the second question, the problem is who dominates. Remember, if you are going to use OpenCL, it's because you want to do this on an hybrid processor. So essentially, what you want to do is to actually go to a GPU or an FPGA or something like that. But the problem is that to move that amount of memory, you actually go to the I/O system, actually send it over the PCI. So get on the other side, you actually have to execute the kernel and get the data back. So that's 2 round trips. We are moving at the speed of electricity. So for the amount of time that you need to do that, it's actually very high. So the threshold, the page has to be so big that it has to span multiple, probably half a gigabyte to actually make any difference between the two. Anyone else?
We're actually almost out of time.
So, we are.
Yeah,
Well,
thank you.
guys, thank you very much for coming.